I'm going to be speaking to you guys today a little bit about Mac, EFI Rootkits on Mac. So first off, I'm Lucas or Snare. I live in Melbourne. I work for Assurance, for a pen testing company. That's pretty much it, like network and stuff. So that's just that. So a few things I'm going to talk about today. First, I'm going to go through just some basic concepts about how EFI works, what it is, how it fits together, and sort of how we can attack that sort of stuff. Actually, before that, I'm going to talk about some of the reasons that I'm here, basically. So, what my goals were when I started to start off this research and what I kind of wanted to do with what I've done. How to do some bad stuff with EFI, like how to attack FileVault for this encryption, and how to actually kernel, and so just some of the fun stuff we can actually do when we get execution in EFI. How we can assist an EFI rootkit on a system through various methods. A couple of cool evil nade attacks can be carried out with physical access via EFI. And then a couple of slides on defense because no one cares about that. So, the reason we're actually here is because I wanted a cool boot screen on my Mac that happened before the kernel, basically, because I'm a Mac guy, like that kind of thing. So I wanted to have a bit of snare and a bit of graphics stuff in the pre-boot environment. And I sort of dug down and know that okay, this is thing called EFI that apparently runs the firmware on the current Macs. So that's where I need to be looking. Very little knowledge of firmware, stuff, BIOS stuff, and any of that. It's all over shit. So it was a pretty massive learning curve for me. It was pretty cool. So I did a bit of research on this about, after I read about 3 words on there's probably actually a lot of potential to do some bad stuff in firmware, right? Because you get execution before the kernel even has been loaded, before disks have been discovered. So there's lots of cool shit you can do. But of course, people have done this kind of thing before. So looking back, we've got quite a few different attacks that have been carried out against firmware and BIOS stuff over the years, right back to the old NBR viruses, which are essentially attacking the bootloader that's stuck on an NBR disk, patching that and using that to attack the kernel, other aspects of the operating system, whatever else. And then right up to fairly recently, in the last 5 years, there have been a few interesting presentations and bits of research about EFI in particular and other BIOS attacks, like John Eaton from NGS did a great presentation at Black Hat a few years back, the possibilities for EFI firmware attacks. The guys from More Security did some great work on BIOS infections around the same time, a couple of years later. The guys from Invisible Things Lab did a really cool attack, getting code execution in the early stages of the EFI. UEFI ruler at the time on an Intel dev board using a bug in the PNG renderer in EFI, which was pretty damn cool, and I used that to reflash the BIOS on a PC board. And using very recently has done some really cool stuff with BIOS as well. And speaking tomorrow afternoon, so I highly recommend you check out his talk because it's pretty awesome. And he's got a Black Hat as well. So he's basically talking about a full replacement BIOS. What is it, hundreds of different boards using core boot that does bad stuff, and it's pretty awesome. So the basic goals that I set out to achieve when I figured out that I could actually do some cool shit with EFI were to be able to backdoor a machine, obviously, gain privileged access, come back later and run some shit, typical rootkit ideas. Preferably be able to persist forever without, cross reboots, but also across replacement of the disk or something like that, because we're talking about firmware, so there's quite a few opportunities to actually write stuff into chips on board, come back later and dude's formatted his laptop because he starts about it and he's still owned, so I thought that would be pretty sweet. And to be able to actually kernel at boot time, because I've done a little bit of work with Mac OS kernel rootkits before, so I thought it would be kind of cool to be able to jam kernel rootkit in at boot time. And to be able to work regardless of all this encryption, because we're getting execution before the disk is decrypted. So anyone that has any sense will have full disk encryption on their laptop these days. So it's kind of part and parcel of the whole attack scenario. Yes, that all sounds like a pretty tall order, I guess. It was kind of hard. Sorry, I was 10 minutes ago when my boss called me because I slept through my alarm. So, some EFI fundamentals. EFI was developed at Intel quite a while ago. I think it was originally started in the late 90s or something. And it was basically Intel didn't think that the current implementation of the BIOS was particularly good. There were heaps of different implementations by different vendors. There were lots of limitations like railroad sucks and lots of other things. So they decided that it would be a good idea to build something new to replace it, preferably to become a standard to replace the BIOS and everything. But mostly just for their upcoming server hardware and that sort of stuff. So it was initially called the Intel Boot Initiative, IBI, and then they quickly realised that it was probably not a good name if they wanted to actually get other people to adopt it without their fucking company name in the name. So they renamed it to UEFI and they handed it over to an open source group called the Unified EFI Consortium. And from then on it was developed as an open source project with a whole bunch of people involved, but it's still mostly an Intel thing, I guess. So Apple's version of EFI, they got in on this pretty early because I don't even remember when it was that they moved to Intel, I guess it's like 5 or something. At that point, that they would have been talking to Intel about building new boards and shit, and Intel would have basically said, here, you should probably use this. It's pretty sweet. So Apple's version is a very early version of EFI. That have been made in UEFI since then, and Apple have kind of gone off and done their own thing and added a lot of stuff they've kind of reinvented a lot of wheels, or forked and implemented a lot of stuff that the actual open main branch has implemented as well. So it's an interesting mix. So it's actually used on all Intel Macs. Every Intel Mac has EFI. There are a few 32-bit versions, but everything's pretty much 64-bit now. And it's also used on a lot of current and future PC motherboards as UEFI, and it looks like your normal BIOS because they stick the same sort of UI on top of it, or they'll do some HII stuff, which I might mention a little bit later. There's also the compatibility support mode, CSM, which basically emulates the legacy BIOS, so you can have a UEFI machine and you can boot an MBR disk on it pretty easily because of the CSM. So that's what Boot Camp is basically. It's Apple's implementation of the CSM. So a little bit of architecture around EFI. So it's a pretty modular system. It's designed with a driver model because writing code for BIOS is pretty shit because you've got to write 16-bit real mode assembly and cram it into the image or whatever, unless you're the vendor. But EFI has a very modular approach, so it's made to be able to easily develop modules for it that work on any implementation of EFI because it's all a standard API. So it comprises basically a core set of components that are all the same sorts of modules. There's like the core components that make up the early stages of EFI boot, and then there's a few applications like the shell, which aren't on every implementation, including Apple's doesn't have the shell built into it, but like VMware's implementation has the shell built into it, so it's kind of like command shell. It actually looks a lot like DOS, which kind of sucks. There's drivers and then there's bootloaders. So drivers, obviously, same concept as in the OS. They support hardware and they give the rest of the software a standard interface to the hardware. And bootloaders obviously load operating systems. So the core components that actually are needed to initialize the disk in the first place and get shit going all reside on firmware. So there's a firmware EEPROM on the board, like the BIOS EEPROM, that holds all the core components and a set of core drivers that will support the basic hardware that's on the logic board. Applications and other third-party drivers can either reside on the flash with those guys or potentially on disk on the EFI system partition or on on the firmware data flash or on option ROMs on PCI devices, which is kind of neat. So PCI devices have a little EEPROM on the board so that they can provide a driver to the operating system to tell it how to the firmware so that it can interact with the device. For example, if you need to boot off a SATA adapter and the firmware doesn't have a driver that tells it how to talk to the SATA adapter just gives it a driver and says, I know your EFI, here's an EFI driver that tells you how to talk to me so that you can read data off me and boot an OS off, right? So that's kind of useful as well. So there's a bunch of, basically like EFI doesn't really support linking at all for like everything's, dynamic linking and loading, everything's statically linked. So there's these giant table structures of all the pointers to all the function calls that are necessary to like allocate memory and find protocols to interact with and stuff in the pre-boot environment. So there's a system table, which is this core table that sort of has pointers to all these other tables. And then there's the boot services table, which contains like a whole bunch of functions for getting shit done in the pre-boot environment, and just in the pre-boot environment, no interaction with the operating system basically. So stuff like allocating memory and finding protocols. And protocols are basically just like blocks of functionality that drivers implement. So like this is simple text input protocol is the protocol that handles console input. And also, so boot services also supports loading other images, that sort of stuff. So the next one is the runtime services table, and runtime services is a little bit different. It provides functions that are available during pre-boot, but it also provides stuff that can be accessed from the operating system. So you can actually call back into EFI from the operating system, the same sort of way that you do with a BIOS with interrupts, except it's not quite the same, but it's the same concept. So runtime services provide time services and virtual memory stuff for like converting addresses between physical and virtual during the kernel, the bootloader to kernel transition when it's, the bootloader builds a memory map and hands it over to the kernel. So it's got to give drivers the opportunity to convert their own addresses over to the virtual memory map that's used by the kernel so it can control them. It does other stuff like resetting the system, managing capsules, which are used for passing firmware updates and other sort of stuff back to the firmware from the OS. And it also has functions for controlling EFI variables, which is what the NVRM utility on macOS interfaces with. So it talks to IOKit, and IOKit talks to the NVRM flash and stores data on those. So that's where your boot device is stored and where the computer name is stored, and stuff that makes the Mac experience a little bit more seamless. So you reboot and your volume's down, so it turns the volume down and shit like that. Yeah. So, and we're actually going to use the NVRM variables a little bit later on when I do some demonstrations and stuff. The configuration table, that's not that important. Whatever, I've got a lot of slides to get through. So, when we're developing for EFI, we use Intel's EFI development kit, EDK2, which is an open source project, but it's pretty much an Intel thing. A lot of dudes, at Apple, and you see lots of device manufacturer email addresses on the mailing lists. But it's mostly an Intel thing, right? So it includes Tiano Core, which is Intel's reference implementation of EFI. So EFI is it's a specification, right? It's not really a product. It's a specification for a firmware interface. Hence, extensible firmware interface. So Tiano Core is basically Intel's reference implementation and their preferred implementation. So they say that they want other people to implement and build on top of. So it actually, contains most of what Apple uses and what most of all the other independent BIOS vendors actually use in their implementations as well. So it's a good place to find bugs and that sort of stuff if you're interested in that. It's written in C, which is awesome because I know C and I like C, and it's much better than writing real-mode assembly, so it's good. EFI uses a whole bunch of existing not old formats, but sort of solid, well-known formats for its stuff. So it uses C and it uses PE executable. So when you build an EFI executable, it's a PE executable. It's a subset of PE32 plus sort of thing. It's actually a pretty gigantic development kit as well. So code that makes up EDK is using that really unscientific method of calculating the lines. It's about 2 million lines that aren't blank, basically. It's a fair bit of code. So it's about twice as many non-blank lines as the macOS kernel. So that's pretty huge. I think it's about a fifth of the size of the Linux kernel, but whatever. Also, sort of indicating how giant it is the specification itself is like 2,200 pages long. And that's just the core protocols that make up the sort of real basic EFI stuff. There's a whole bunch of other documentation that specifies all these additional protocols that do different things, and documentation for the firmware file system formats. And there's hundreds and hundreds of documents produced by Intel about this, describing parts of this system. So it's pretty huge. A couple other things that just indicate how gigantic it is some of the protocols that you can see there that are implemented by the basic like core EFI specification. So there's stuff for disk and file system access, console input and output. That's fairly obvious stuff, but like full
full screen graphics stuff. The HII library actually, has stuff for building forms and fancy UIs, which is what, you see like the ASUS BIOSes and the AMI BIOSes that have like, cool tab interfaces and stuff. That's all built in HII. Every network stack under the sun. There's even like user management and crypto stuff, which is pretty hilarious. Like it has an IPsec stack, and it has implementations of all the crypto algorithms, which is mainly aimed at doing secure boot, which I'll mention a little bit more about later. But there's heaps and heaps of stuff in there. It's a gigantic specification. It's really starting to sound like someone's put an OS in my firmware, right? Which means that there's going to be shitloads of bugs, and people have found stuff already. But I think it's going to be a gold mine of really fun bugs. So this is basically what the boot process looks like with EFI. This is lifted straight from Intel's documentation, hence the shitty low quality graphics there. Whatever. I suppose I should talk through that. So there's the few core phases of EFI. There's the security phase, which is basically just sort of establishing a root of trust for the system and doing some really low-level initialization. And then there's PEI, which is the pre-EFI initialization, which does the majority of the initialization of the CPU and chipset, all that sort of stuff. And then there is the DXE phase, which is mostly what we're interested in. So that's the driver execution environment, which is where drivers get executed, funnily enough, the environment in which they are executed. And that's, so during that stage, drivers are loaded from wherever they're going to be loaded from, and they're executed, and they get their tentacles into the EFI environment. So following that, DXE hands off to the BDS phase. So when you hold down the Option key on a Mac and you get the little boot menu, that's BDS, which implements just the boot device selection, the bootloader, and continues on with the IDA's not real good at, doesn't know anything about like what all within EFI. So I wrote some little IDA Python scripts to work out where the boot services table has gone and where it's been stored, what data it's been stored in, and then sort of reassign all the function calls basically to boot services and runtime services. So takes your code and makes it look something like that. So that's, if you're looking at reversing EFI, it's probably a good starting point. So on to the fun stuff, doing some actual bad stuff with EFI. There's plenty of options for what we can do. As I said, the modularity and the SDK make it a pretty nice platform to develop for, relatively compared to traditional BIOS stuff. So basically what we want to do is build a driver, a malicious driver that's going to do some bad stuff, get it loaded fairly early on in the boot process somehow, register our callbacks, hook some boot services and runtime services, and just generally screw with what EFI does, hook some protocols. As I say, no 16-bit real mode assembly. It's all C, depending on what you're doing, I guess. And there's a generic interface because it's all specified. It's in the shiny PDF. So this is the first thing that I thought I'd look at was attacking whole disk encryption, because that's obviously going to be a pretty massive win. So there's my fancy hard disk thingy. So that's what this kind of looks like without FileVault in a default install scenario. You got the EFI system partition, which is a 200 meg-ish partition at the start of the disk. It's part of the GPT format. Then after that, you got your OS partition, which has got all, the entire OS on it, basically in Mac OS, and the bootloader in system library core service is boot.efi. And then you've got at the end of the disk from line onwards, you've got the recovery partition, which is when you hold down Command R, you get to the little recovery thing that lets you reinstall your OS. That's on the recovery partition. So if we encrypt the OS partition, and that's where the bootloader is, like GPT doesn't have an MBR or like anything like that. So we need somewhere to store the bootloader. So basically what Apple have done is just move the bootloader to the recovery partition. So when you boot a FileVault encrypted machine, the actual boot target is the recovery partition, and then the bootloader goes, okay, well, this is a FileVault machine, so I need to prompt for the passphrase. So that passphrase entry screen is part of boot.efi, prompts for the password, user enters their password, and then it finds the encrypted partition and decrypts it, and then loads the OS. The kernel cache is what actually gets executed by the bootloader, and that's actually also stored on the recovery partition. And that's basically just for improving the performance of the boot process. So all of the kernel extensions just get stuffed into this big kernel cache and then stuck on the recovery partition. So you probably would have messed with that stuff if you built a Hackintosh, because you got to do some ungodly things to the kernel cache. So when you boot an EFI machine, a FileVault machine, basically what I just said happens. Platform firmware initializes, loads the bootloader from the recovery partition. Bootloader prompts the user for the passphrase, unlocks the disk, executes the kernel. Pretty straightforward. So the obvious thing that we want to do is steal the user's passphrase, right? So we can steal their laptop later and decrypt their disk. Or, we may have, not we, but some bad guy may have broken into their hotel room and imaged their machine and needs to get access to that image. So they want to steal their passphrase. So they backdoor their machine, and this happens, right? So we want a keystroke logger in EFI. So pretty basic concept. We hook some function, and then when it gets, key gets pressed that calls that function, we log it and then call the real function. So that's basically what I've done for this guy, is we hook the simple text input protocol, which is the console input protocol for EFI. Specifically, we need to find the console device handle and then sort of walk that and find the instance of the simple text input protocol. And we just overwrite the pointer to the read keystroke function with a pointer to our function, and then our function logs it and calls that function. So that's pretty straightforward. There was a few little hitches in implementing that, because when the driver gets loaded, the console hasn't been initialized, so there's no read keystroke function, there's no console, there's no instance of the simple text input protocol on the console device handle. So you've got to actually register some fancy protocol installation notifications and just wait around until it actually gets added to the device handle and then called back into and stuff like that. But it's a pretty basic concept, and that works pretty well. I guess there's another option which I haven't really looked into, is just actually stealing the AES key out of memory. So we could actually hook the load image protocol on and mess with the bootloader. That's probably requires a little bit more actual reversing effort of the bootloader. But fortunately, Apple's been really nice with leaving some debug logging in the bootloader. It doesn't actually log that stuff, so there's I couldn't find any flag to enable it, but there's heaps of stuff in there that's just tells you exactly what their functions are called, which is really nice. So the real fun stuff comes with basically attacking the kernel, right? So the goal of this is my reused slide from KiwiCon last year. Thanks, guys. The real fun, the real goal of a low-level rootkit is going to be to attack the kernel, right? We want to patch the kernel and interfere with the way the operating system actually works and steal data and do other fun stuff like that. So, what can we actually do from EFI? We can do quite a lot of stuff. So we want to patch the kernel from EFI. So the way that we're going to do this is we're going to find some place to put some code. We're going to hook some kernel functionality, I guess, something like that, get execution during kernel initialization, and then we're all good because we've modified the way the kernel starts up. So the first problem is it's not loaded when our driver gets loaded. So we've actually got to, even during most of the phases of DXE, right until the very end, the kernel isn't loaded. So DXE goes through its initialization, and then BDS happens, and the bootloader gets loaded off the disk, and the bootloader loads the kernel. So we don't get any opportunity to do anything during DXE. So there's this neat function called exit boot services, which has been basically put there for drivers to register for exit boot services, and then it gets called just before the kernel is executed, allowing drivers to clean up the memory that they've allocated and convert all their pointers to the virtual memory map and all that sort of shit. But it's actually really good for us because the kernel's been loaded into memory at this point, so we can mess with it. So a slightly more detailed EFI boot process from one aspect is so the first phase there is the basic platform initialization stuff. So sec, PEI, and DXE, whatever. So DXE loads the drivers from loads our malicious driver from an option ROM or from a off disk or whatever. Hands off to BDS, which loads the bootloader off the disk. The bootloader loads the kernel, and then prepares the environment for kernel execution, which is basically what I was just talking about. So it cleans up its memory and gets ready to hand off to the kernel. And then at this stage, like during this environment preparation phases when exit boot services gets called to tell drivers to clean up their mess, and then the kernel gets executed. So that's kind of where we're going to jump in and start screwing with the kernel. So the next thing we need to do is find where the kernel actually is going to be in memory, which was surprisingly easy because it obviously, not obviously, but it uses basically the same memory location as it would in the operating system. So looking at the kernel image itself with OTool, we can see that the VM address of the kernel image, or the first segment of the kernel image, is going to be at that 200K hex address. And if we look at that in the debugger in a live operating system, we can see that the Marco magic number, feed face or feed face plus plus for 64-bit is right there. So yay, that's where the kernel is. So in EFI, EFI actually uses a 32-bit like flat memory model. Uses a different addressing mode too, but it doesn't use real mode. So in EFI mode, in EFI's 32-bit mode, we just truncate the address basically, and it's at that 200K hex address. So that's actually where the kernel image starts in memory in EFI. There's no address randomization or anything like that, so it's all good. So what are we actually going to do? We're going to inject a payload into the kernel somewhere, patch some kernel function somewhere, and point it to the payload. What I've implemented is basically using a bit of a trampoline payload to load a full rootkit payload later on. So the trampoline payload, jumps off to a big payload that's stored in like an EFI variable, or potentially, some EFI runtime services memory, or even, over the network or something, because EFI has, cute network stacks and stuff, which is awesome. So where can we actually put our payload? I just used the old, Silvio page alignment padding technique. So the end of the text segment of the kernel binary, there's a bunch of padding because all the segments are aligned on page boundaries. So there's some padding there. Apparently on the default 10.7.3 kernel is almost an entire 4K page. I think that changed in 10.8.1. I haven't looked at 10.8.0. I haven't looked at 10.8.1, but there's like I think it was only like 300 or 400K or something. But still, it's still loads to store a basic little trampoline payload, which is all we need to do at this point. Sorry, K bytes. I mean bytes. 300 or 400 bytes. So at this stage, we've been called by exit boot services. We know where we can store a payload and how much space we have. What are we going to put there? And then how do we get it called? I'm going to answer the second question first, so which makes more sense. How do we actually get it called? Well, what we're going to do is we'll patch a function in the kernel's boot process. And I chose to use to load an init program, mostly just because at this sort of stage, all the kernel subsystems have been initialized and everything's kind of ready for serious business operations. So, because we're about to execute the init process, which is what that function does, load an init program. So just use a typical inline function hooking technique and overwrite the first few bytes with a jump to our function and store that jump in the payload so that it can restore it later on. So what we're going to put in there is a trampoline payload, as I just said before. So it's just a little payload that saves the state of the CPU, locates its next stage payload somewhere, stored in an EFI variable in this case, calls the initialization routine of that next stage payload, restores the patch instruction that we used to get execution in the first place so that we can jump back to the kernel and let it continue without crashing, which is probably good. restore the state of the CPU, jump back to the batch function, and then the kernel continues booting like nothing has happened and everybody is owned. And that's basically a diagram of what I just said, so very useful. There's a little code snippet of actually preparing the trampoline code. So we basically just find the load init program symbol in the kernel, save the 8 bytes or whatever at that address, and then build an E8 like relative jump to that address, and just overwrite. To our payload, and just overwrite the first instruction there with the E8 relative jump to our payload. And then we copy that into the kernel and we win. So once we're actually inside the kernel, I'm not going to go into this too much. There's been a lot of stuff covering macOS kernel rootkits over the last few years. In fact, someone released one fairly recently. Check out those resources. Basically, I've written a few little bits and pieces on my blog about it. Nemo's done some cool stuff over the years. Dino Dizovi's done some cool stuff. Fractal has done heaps of awesome stuff. He's a really smart dude. Definitely worth checking out his stuff. So we can hook syscalls, we can install network kernel extension, callbacks, to get called into when packets arrive and stuff, and I send out and stuff like that. We can install trusted BSD policy handlers, which is kind of a neat way of getting building an interface to your rootkit without using syscontrol or hooking syscalls and other stuff that people are obviously going to look for. It's still relatively easy to detect, but it's a little bit more obscure than the traditional syscall hooking techniques and that sort of stuff. And we'll patch all the bits and pieces in the kernel and do all the typical badness that kernel rootkits are going to do. So the demonstration I'm going to do will use the just hooking the kill syscall. So we overwrite the entry in the sysint table to a pointer to our function, and whenever the kill syscall gets called, our function gets called instead. So if we give it a magic, signal number, then the kill syscall, our kill syscall wrapper, just elevates the given process to UID 0, and then calls the kill syscall normally, so everything works. Okay, so onto persistence. There's a few ways of persisting an EFI rootkit on a Mac. So in ascending order of awesome, we've got patching and replacing the bootloader. The reason that's not particularly awesome is because it's on disk. So if we're on disk, we might as well just patch the kernel or whatever. Following that, we've got the EFI system partition, which is slightly more awesome because we can do a couple of cool things with it. Then we've got PCI device expansion ROMs, which is pretty sweet because we can persist across reboots and so across disk reinstalls and shit like that. And the firmware flash is obviously the ultimate goal because then we're alongside all of Apple's shit and we can do whatever we want. So yeah, a little bit more detail on those. So as I said, if we're patching boot.efi, we might as well just patch the kernel or something like that. It's probably a little bit more difficult to detect actually patching the bootloader, or probably not something that Mac users are going to look for. But yeah, we could also just install a kernel extension. So there's, it's not a lot of benefit in doing that. It is somewhat useful for evil mate attacks, just because the bootloader is on an unencrypted partition on the disk. So you can just patch it if you have physical access to the machine. Although that's much more difficult with the current range of machines because everything's all soldered and glued together with a big pile of hot glue. Not really, but So I give that a 4 out of 10. It's not great. Oh yeah, cool. I was like, for a second there, I thought I was using a different set of slides, which would not have been good. So EFI system partition, I initially wasn't too impressed with because it's meant to be for storing drivers. So according to the specification, you should be able to stick drivers on the ESP in a specific path, per vendor, and it'll get loaded at boot time. But Apple's implementation doesn't actually do that at all. So you can't just stick some stuff on the ESP and have it loaded. But I did find another use for the ESP, so I've slightly revised my opinion on this. So you can set some NVRAM variables in such a way that you can boot from the ESP, which is basically what happens when you install refit. No one actually tells you how to do this, including the refit developer, but he says it's, you can do it if you know what you're doing. So basically you've got to use bless in a specific way to install refit or refund, which are just EFI bootloaders, to the EFI system partition, and then tell the system that it needs to boot from those first. And you do that by configuring some NVRM variables that sort of point the bootloader, the BDS phase at where the next stage bootloader is going to be. So we can actually force Apple's EFI implementation to use it, and I'll demonstrate a way of doing that a bit later on. So I'm going to revise my opinion on that and give it a 5 out of 10. It's all right. So PCI expansion ROMs, I'll just explain a little bit more about how this works. So basically when the bus is initialized by the PEI phase, the DXE phase of EFI, all the devices on the bus are probed for their expansion ROMs. So any expansion ROMs are discovered, and then they're mapped in a memory, and then the DXE phase loads any EFI drivers that were found and just executes them. So it's used for things like SATA adapters, as I mentioned before, also like Ethernet adapters. So Pixie firmware, like that will be loaded on an EFI system, the expansion ROM on the Ethernet device, and executed, and that's how you get your Pixie boot stuff. Also EFI and BIOS drivers for graphics adapters. So most serious business graphics cards have an EFI, have an option ROM with an EFI or BIOS driver in them, in order to allow a system to interface with them if that system doesn't have that particular driver in its firmware image, which is probably going to be the case because there's so many fucking graphics cards. This is kind of hardware specific, so actually attacking these is kind of hardware specific because it depends on the particular chipset and the particular flash chip and how you interface with them. But Apple's got a fairly restricted set of hardware, so it's not that difficult. So graphics cards in iMacs have option ROMs. So MacBook Pros with discrete graphics cards have option ROMs. I believe there's an option ROM on the somehow on the on-die Intel Graphics HD Graphics 4000 stuff that's on the new Ivy Bridge processors, but I'm not sure how you could actually interface with it because it's on-die. But there does seem to be some sort of driver provided by that, so that could be an interesting place as well. So we can write to them from the operating system usually because you've got to be able to update your graphics card firmware. So ATI provide tools for it, NVIDIA provide tools for it. There's GPU-Z and stuff like that. Lots of like pro gamer tools for tweaking your graphics card that you can use to reflash them. And yeah, you can if you reverse Apple's firmware updates and stuff like that, you can figure out ways to do that yourself. So that's pretty cool. I give that a 7 out of 10. It's pretty sweet because you can persist across, pulling the hard disk out and putting it back in. But it's a bit easier to detect, I guess, than firmware flash. So firmware flash, writing to firmware flash is pretty awesome, ultimate goal. So it's hardware specific, but there's only a limited set of them, and it's always there because it's got to have an EFI firmware flash. So if we can write to the firmware flash, we can do just about everything. What I attempted to do was replace it, add a driver to the firmware flash, and then reflash it with flash ROM, which you can't actually do on later systems because they do use system management mode and the write protect flag on the firmware flash appropriately. But the earlier systems they did not do that. So if you want to reflash, you've actually got to do it from EFI, go into system management mode, and then reflash. But it's all doable. So that's pretty sweet. There's one problem with that though. Apple actually checks the signature on the firmware image. So if you mess with it, you can't actually do it. And I bricked the machine doing that, which was awesome. So it's probably a little bit easier on systems that don't do that. Yeah. So a little bit about Apple's firmware updates briefly. The way that they, I'm going to skip through this because I have too many slides. They basically copy stuff to the ESP and then they reassign the bootloader to point to the firmware updater, and then they reboot, and then on the next boot the firmware gets updated and then it reassigns it back to the bootloader and boots the system again. Telling it where to boot isn't really a big problem because if it can't find anywhere to boot, it'll start enumerating the disks and finding the bootloader. Really the NVRM stuff is just to make it quicker so it knows exactly where to look first time. Newer machines use capsule files, which I mentioned before, which loads it into memory at a specific address, and then reboots the machine, and then it does a warm reboot without actually resetting the RAM, and then EFI knows where to look, and it loads that capsule out of memory and dispatches it. The specifications for the firmware file systems are actually available from Intel, which is kind of nice. If you saw Igor's talk about the AMD management engine stuff, like it's kind of similar firmware file system formats to that. It's all specified by Intel, yeah, it's nice. So there are a bunch of tools out there for manipulating them, these firmware images, but they're not particularly good because they're kind of aimed at, like, stealing Windows or messing with ACPI tables for Hackintoshes and that kind of stuff. So I had to build some new ones, which I haven't released, but there's a couple of other ones out there which do sort of similar stuff now. And one of the great things about EFI for a reversing perspective is, as I said, they're PE binaries, so IDA Pro actually will understand them. Yeah. So that's basically like what the output of my tool looks like, which is, there's a few like it now, which is pretty neat for actually disassembling EFI firmware flash binaries. So this is what happens when you do accidentally overwrite the firmware with an invalid image, and you have to pull the board out and then use IC hooks to hook onto the leads on the 8-pin DIP package that contains the firmware flash and reflash it with a bus pirate. Surprisingly enough, that actually worked, and that machine now boots again. So I was pretty stoked with that. Yeah. So that was like an old 2007 MacBook. Okay, so a little bit about evil mate attacks. I'm going to run out of time, so I'm going to have to smash through this stuff pretty quick. But there's a few possibilities, basically. So the first one is pretty easy. It's kind of like what script junkies like Pixie Boot, what was he call it? Pixie Exploit attack does. So you change the boot target. You provide a malicious image over the network, or you hold down the option key and you plug in a USB flash drive and you boot from that, and that does some stuff when it boots, right? You can actually pull the disk out, plug it into another machine, backdoor the bootloader, whatever you want that way. And then there's a new attack vector, well, not new, but like new from a Mac perspective, which is Thunderbolt, and that's something I'm going to talk a little bit more about because it's pretty neat. So what can we actually do with Thunderbolt? Well, Thunderbolt is basically just PCI and DisplayPort, like glued together and stuck in a chip. So the Thunderbolt port on your Mac, there's a chipset, like Thunderbolt controller at one side, and then the Thunderbolt device has another controller, and it just crams PCIe and DisplayPort together, and then they're split out at each end. Just like that fancy diagram. So Thunderbolt is PCIe, right? And PCI devices, as we already know, have option ROMs. So many Thunderbolt devices also have option ROMs, and this is useful. Some express card adapters have option ROMs. So I found a couple of SATA adapters that have option ROMs on board. So like if you have a SATA adapter and you download the RAID firmware for it, that's going to be an option ROM that's provided to the OS so you can boot from that RAID set, right? So this was my initial Thunderbolt evil mate attack little toolkit, right? It was an express card to Thunderbolt adapter, a Thunderbolt cable plugged into the Mac, and then a SATA express card adapter plugged into that with an option ROM on it. So you plug that in at boot time. So you plug that in, power the machine on, driver gets loaded off the SATA adapter, and then you get execution in EFI, right? So I thought that was kind of cool. And then shortly after that, Apple came out with a whole bunch of new machines that didn't have Ethernet on board. So they distributed these little Thunderbolt to Ethernet adapters. Turns out they have an option ROM on them as well, which is kind of sweet. So it's a Broadcom chipset with a 64K EEPROM on there with an option ROM. So you can store your EFI badness on those. So basically the process for attacking a system looks like this. But before that, the reason for actually using Thunderbolt for this is that if you have an EFI firmware password on a Mac, that basically stops an attacker from changing the boot target and changing other things about the boot process. So if you hold down the option key and you've got a firmware password and you can't change the boot target unless you enter the firmware password. Historically, there have been a few ways of, I'll talk about that a bit later anyway. But yeah, so that's the main reason we're actually attacking stuff with Thunderbolt, because you can't do those evil mate attacks if anyone's got their machine configured correctly, right? So this is kind of what the attack process looks like. So, we start off, we attach the Thunderbolt adapter to the machine, we power on the system, the driver gets loaded from the option ROM in the adapter, it deploys the payload, which, executes the driver. The driver, in the example I'm going to use, just drops a shim bootloader onto the disk, and then, points the NVRAM at it to boot from it. And we could potentially also flash the payload driver to an option ROM on the graphics card or something like that that's actually internal to the machine. And all this happens before the FileVault passphrase entry screen has even appeared. So we've got execution fairly early in the boot process of the machine, which is pretty sweet. So if we look at this guy with LSPCI, we can see the expansion ROM described there. So it's a 64K. It's at that address, whatever. The EDK actually provides some nice tools for building, ROM images from your driver. So you build a driver and then you can build an option ROM image from it, just using their tools, which is pretty sweet. And then Broadcom nicely provides you with a tool for flashing the images onto their Broadcom devices, which has to be done in FreeDOS. Well, I had to do it in FreeDOS. They also provide an EFI flasher for it, but it's only for IA64, which is kind of lame. So I'm going to do a couple of demos. Actually, it's on okay for time. I'm going to do a couple of demos quickly. Firstly, I'll do an evil made demo just using like an emulated option ROM. So VMware has virtual Ethernet adapters, right? And they actually have virtual option ROMs on them so that you can, provide your VMs with Pixie firmware, which is kind of hilarious. But I'm going to use that for a demo so I don't actually have to flash something because I don't really want to explode any of my machines if I fuck it up. So assuming we've already got privileged access through some other vector, if we've owned WebKit, we've escaped the trusted BSD sandbox, and we've elevated our privileges to root somehow, so we've got root access on the machine and we want to install a rootkit to come back later and keep owning the machine, stealing data, whatever. So if we've overwritten an option ROM in the machine with our own malicious device driver, EFI device driver, when we boot the machine, as I said before, the PCI bus gets enumerated, all the devices get asked for their option ROMs, the virtual PCI bus in this case. The driver is loaded from the option ROM, and for demonstration purposes, as I said, I'm going to use the virtual Ethernet adapter, but in practice you probably would use something like the graphics card because it's they're on everything and they've all got option ROMs. The driver registers for the exit boot services callback. The bootloader is executed, which loads the kernel. The driver gets called into exit boot services from exit boot services and then patches the kernel, and then the kernel's booted and everyone is happy. Mostly the attacker because they have root. And I'm going to do a second demonstration, which I have to do afterwards because I've got to unplug my machine and like hold it up so you can see it, which kind of sucks. But I'm going to basically do the evil mate attack that I talked about with Thunderbolt. So we connect the Thunderbolt gigabit Ethernet to Thunderbolt adapter to the machine. We boot the machine, driver gets loaded from the adapter's Pixie firmware section of the NVRAM and executed. The driver actually is going to write a shim bootloader to the ESP on my disk here, and then configure the NVRAM to point at that bootloader instead of the main system bootloader. So after that, when on every subsequent boot, when the machine starts up, the NVRAM tells it to boot from the shim bootloader, and then the shim bootloader actually gets executed before boot.EFI, and that's going to load, the payload driver or whatever, which probably registers a callback for exit boot services. Shim's the shim executes the normal bootloader and everything carries on. Awesome. Except I'm not going to do any of the kernel patch stuff because it's too hard to hold up the screen for that long. So basically, I'm just going to it's going to show a cute boot screen and then move on just to show that it's got execution before the bootloader. Yeah. So I'll do a demo quickly. Hopefully this works. Hopefully I'm pretty sure I remembered to install my option ROM first. So let's just see if this works. So basically, nothing is really I'm not really going to do anything to make this happen because we're going to assume that at this point, as I said, the option ROM has been overwritten by a malicious driver. So let's just boot the machine, and if you watch, you'll see a quick flash of what looks like exploit output with a whole bunch of little square brackets and pluses, and that's actually it, the driver itself patching the kernel. So, that's not really, oh, hey, it's not there, okay. Wait a minute, I'm an idiot. So, one sec. I meant to do this morning, and then I slept through my alarm, and my boss woke me up, as I said. So, let me just, God damn it. Oh, I get it. I rebooted my machine. It was in /temp. I'm an idiot. Okay, one sec. Let me make a new one. Yeah. Sorry? No worries, man. Sorry, guys. One sec. Man. All right, you know what, I'm going to skip that demonstration. So here's something I prepared earlier in case my demonstration didn't work, which is what's happened, and I need to reset my display here. Yeah, because I'm an idiot and I forgot to build my option room. But that's okay. So...
Just imagine that it was an awesome demo.
So there's my my boot screen that would have appeared, and then there's the kernel patch little scenario that would
There you
happen.
go.
All right, so I'm going to talk really quickly through defense because I've got like 3 minutes left. Yeah, so EFI firmware password, as I said, is going to prevent some evil mate attacks. It kind of sucks, and there's a few ways to bypass it. Like there's the old like pulling a stick of RAM out and then flashing the NVRAM trick, which used to work but doesn't really work anymore because the RAM is soldered onto the board. So it also doesn't prevent flashing option ROMs. It doesn't prevent loading devices over Thunderbolt, which I'll show you in a sec. As I said, there's a few ways to remove it. So it's not really a great mitigation, and I think Apple can do a much better job of preventing these kinds of attacks. UEFI Secure Boot, which I haven't talked about at all and should have talked about a lot more, but it's basically a specification for driver signing within the EFI environment, and it's something that's definitely going to help with a lot of these kinds of attacks. There's a few boards starting to emerge, that support it, and there's been a lot of work in the Linux community to support it and not let it break, everything, the entire world explode, etc., because everyone's really upset about Microsoft's, grand decrees about it. But yeah, so basically just verifies the signatures of drivers and bootloaders at boot time, so it would stop this kind of attack, basically. There's a few issues with it. Whatever, come and talk to me if you want to hear about it. So basically, I think we're all kind of screwed at the moment with this kind of thing. Glue all your Thunderbolt ports shut, basically. Just, yeah. I think Apple should definitely implement Secure Boot using the TPM, like, any sane person would do. They need to put TPMs back on their systems, though, to do that, which sucks. So all the current systems don't have TPMs. They all did have TPMs for quite a few years, but they weren't used by anything. They took them off because they weren't using them, and now they really need them. So I think that at some point they're going to start putting TPMs back on their boards, or they'll be on die or whatever. Yeah, there's some references. Slides will be up online, so that's basically it. And I'll do a quick demonstration of the Thunderbolt thing now. Just this guy hopefully will work. Yeah. So what I'm going to do is I'm going to take my little Thunderbolt adapter here. I'm going to power my machine off, and I'm just going to kill it. So, running out of time. Die. All right. So take my little Thunderbolt to Ethernet adapter here, plug it in, and I'm actually also I've modified this this attack a little bit to use a USB flash drive as well for payload deployment, so we can deploy much bigger payloads because 64K. while it's plenty to hold a little bit of kernel code, it's not, enough to hold a fully fledged bloatware enterprise fucking kernel rootkit, right? So I've got a like 8 gigabyte USB flash drive here that's got my fully fledged, enterprise ready kernel rootkit on it. Doesn't really, it's got a 900k BMP of the boot screen on it, but whatever. So I plug that guy in. So basically what's going to happen is I'm going to power the machine on, maybe? Yeah, okay. So there's going to be a few delays because I put a whole bunch of debugging code in, but so the Thunderbolt driver has been loaded off the device at this point, and now it's patching, it's enumerating the devices and looking for the ESP, the EFI system partition, and hopefully it looks like it's, okay, so it's writing the payload to the ESP that it's copied off the USB flash drive. So it's sort of gone through and enumerated all the USB devices as well and looked for the USB flash drive with the right payload on it, and then it's copied all that to the ESP, and it's fiddled the NVRAM to now point at my bootloader instead of the system bootloader. So there's my boot screen. So I win. So now it's just going to continue booting right like normal. So that's a normal boot. So now if I remove my attack apparatus here, power the machine off, and put it back in the victim's bag or whatever. So if the victim powers the machine on now, again it's going to take a little while to boot because there's heaps of debug code and stuff in the shim bootloader which I wrote at like midnight last night because I'm an idiot. Sorry? Yeah, I wrote this like last night and the night before, in between bouts of drinking. So it's kind of, and it takes a little while to boot up because there's heaps of I put like stalls in there to, tell me how many times something's fucked up and that sort of thing, because sometimes you don't actually get any visual feedback depending on where you are, and it's kind of hard to debug this stuff on actual hardware. So hopefully at some point there's my boot screen. So back to